So in this video, we are going to discuss about various range of specifications of analog to digital and digital to analog converters. So there are some important specifications of these converters which are specified by the manufacturers. So first one is resolution for this is for ADC. Okay, so the resolution, it is defined as a smallest change in the analog input. Smallest change in the, since it is so here in ADC, analog is my input and digital is my output. So if there is a small change in the analog input for 1 bit change in the, so even for one small change in the analog input, there must be 1 bit change in the digital output, right, at the output, because the output is a digital one. Okay, so if you see, if I consider a 5-bit ADC, okay, so for this 5-bit ADC means, let me explain the minimum values. So the minimum value is sorry, if it is 5-bit ADC, so it has how many intervals? It has nearly 1 divided by 5 minus 1 intervals. That is nothing but 31 intervals. Okay, so what is the resolution? So the resolution for a 10 volt input range. So here the 10 volt input range, it represents the full scale value. Okay, so the 10 volt range is so what it should be measured in terms of millivolt. Those so that is equal to 1 divided by 31. 1 divided by 31 into 10. So it is a percentage. Okay, so what is 1 divided by 31 into 10? 0.322. Okay. So that is equal to, so here it is nothing but full scale voltage. Okay, so if you see, I can write in order to obtain the full scale output. So the full scale output is equal to full scale voltage minus 1 LSB. Okay, so how to determine 1 LSB? So the 1 LSB is nothing but 10 volt. So 10 volt is nothing but my full scale output. Since suppose if the input is ranging from, sorry, my output for DAC. Okay, this is for this entire thing is for DAC. So if my analog output ranges from 0 to 10 volt. Okay, so it's 10 volt divided by 2 power, since it is a 5-bit DAC. Okay, since it is a 5-bit DAC. So I can write 10 divided by 2 power 5. Okay. So that is nothing but so this is for 10 volt. Okay. For 10 volt, 1 LSB is equal to, for 10 volt range, it is equal to 10 volt divided by 256. That is nothing but 10 divided by 32. So what is 10 divided by 32? We know. So this is also approximately you can get 10 divided by 32 is 0.3125. So that is equal to 312.5 millivolt. Okay, so this is your LSB. So suppose if I want to find so here what the LSB means is this is for 00001 input. Okay. Okay, suppose if I want to find it for 10000. So 100 input means, so this is nothing but your MSB. Okay. So if you see, if I want to find the value for the input 00010 input, so you have to multiply this one by 2. Okay. So if I want to find it for 00010, okay, so I have to multiply it by 2. So for this one you have to multiply it by 4. For this one you have to multiply it by 8. For this one you have to multiply it by 16. So you will get 16 into 312.5 millivolt. Okay. Okay. So what is 16 into 312.5? It is nothing but 5000 millivolt. That is something but 5 volt. Okay. So or otherwise, in order to find MSB value, so you can use another formula. So 1 by 2 of full scale value, full scale output, full scale voltage, sir, full scale voltage. So that is something but 1 divided by 10, 1 divided by 2 into 10. So that is equal to 5 volt. So you can do it like that also. So next, in order to get the full scale output is equal to full scale voltage minus 1 LSB. Okay, so here the full scale output is 10 minus 1 LSB. 1 LSB is for this 1 LSB is for full scale value for 10 volt, right? So for 10 volt, so I can write it as 10 divided by 32. Right? So what is the answer I get? Say 10 1 minus 0.031. So that is equal to 9.687 volt. Okay. So let us now come to the resolution for the resolution for DAC. So here given there is a small change in the smallest change in the so since it is for DAC, the smallest change in the voltage, that is 1 LSP, okay, which may produce which may produce which may be produced at the output of the convert. So even there is a small change in the DAC, it should produce us a value. So you can see even for this one also you have to produce some value, right? For 1 0 it has to produce some log output. So this is called as this is about the resolution. So next let me come to linearity. So it is an important measure of its accuracy. So and it also it tells us how it is close to how close it is to my ideal converters, ideal transfer characteristics. So if you see this is my for DAC. For DAC, digital is my input, right? So this is my input and analog is my output, right? So for 0 0 0, it will produce output like this. For 0 0 1, so since it is a 3-bit value, you have to get 1 divided by 7 of 1 divided by 8 of 1 divided by 8 of my full scale value, right? So likewise, if it is 0 0 0 1 0, it has to produce 2 divided by 8 of VFS, right? So likewise up to it has to produce for 111, so it has to produce 7 divided by 8 of VFS, right? So this is my ideal curve. This is how it is. But what I actually get for 0 0, I will get 0. Okay. For suppose instead of I am getting like this. Suppose if I get this is for ADC or DAC. So you can see this is my ideal straight line transfer curve, and this one is called as ideal transfer function. Okay. So this is called as so you can see this difference between this 1 and 2. So this is considered as a 1 LSP, that is ideal code width. Okay. So there may be a change in this value. Okay. So it can go either this way or this way. So this is represented as a quantization error. Okay. So it ranges from 0 to 1 LSP. Okay. But if you see the third diagram, so instead of getting this type of dotted line, I'm getting like this. So though the ideal code with this 1 LSB, so there is a change in the ideal transfer function, right? So this is my ideal transfer function, but instead of getting like this, so it get deviated by this one. So you can see the quantization error is here is plus or minus 1 by 2 of LSP. So this is called as compensated quantization, whereas this one is called as uncompensated quantization. So now let us discuss about 0 and uh, 0 and full scale error, then offset and gain error. So if you see this deviation has happened due to the gain and offsets error. So if you see the static performance of the DAC, which is determined by a fitting a straight line through the measured output point. So the linearity error, which will measure the deviation of the actual output from the fitted line. So and it is given by epsilon divided by delta. Okay, so this error is usually represented as a fraction of LSP increments or percentage of full scale voltage. So root ADC or DAC, which will exhibit a linearity error of less than plus or minus 1 by 2 LSP. So now let us discuss about this 0 and full scale error. So what is full scale error? What is 0 error means? See, this is my ideal transfer function, and this is the dark line is adjustable transfer function. So you can see you have to see the first so it is nothing but a difference between the actual first transition voltage and the ideal first transition voltage. So the first transition voltage is here. So and the adjusted transfer function value is here. So the difference between this one is nothing but a 0 scale error. Okay. So similarly, if you want to note down the difference with what is full scale error means, it has to be measured from 6th and the 7th value. Okay. So from the 6th pin, the actual value is this one, and the 7th pin, the actual value is this one. So this represent the full scale error. Okay. So it is nothing but a full scale error is it is represented as EFS. So it is the difference between the actual last transition voltage and the ideal last transition voltage. So similarly, if I want to find what is offset and gain error means, so we can see this is my ideal transfer curve, and this is ideal transfer function. So instead of starting from here, if it start from this end means, so if you see the curve, so this is nothing but the offset error. Okay. So next, if I want to find the gain error means, so what is gain error? So you can see at the final, okay, at the end point. Okay, so at the end point, if we see, if we measure at the 7th pin, so here I have this value, and here I have this value. So this is nothing but my gain error. So it is defined as a difference in the slope of the actual and the ideal straight line transfer function. The error is not measured as a slope, but rather as a difference in the total available input range from the first to the last conversions between the ideal and the adjusted straight line transfer function. So it is also expressed by EG is equal to E ZS minus EFS. Okay. So next one is differential non-linearity. So there are two critical figure of merits which are used in defining the ADC operation. So one is a missing code. So what is missing code means, an ADC has a missing code if an indefinite, similarly small change in the voltage will causes a change in the results of two codes with the intermediate code never being set. So a DNL of minus 1 LSP indicates the ADC has a missing code. So if you see this 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 diagram, so here you can see this is my the dotted line is ideal curve, and this one is the actual curve. So you can see I don't have the 3 is missing here. So this is a missing code. So if you measure the DNL value, it is nothing but -1. So this represent a missing code. Okay. So next one is monoticity. So an ADC is monotonic if it is continuously increasing conversion, which will results with an increasing voltage. Okay, whereas a non-monotic ADC, which can give you a lower conversion results for a higher input voltage, and which will also means that the same conversion may result from two separate voltage range. So often the transfer function will completely miss the lower code until after the higher code is converted on an increasing input voltage. So this curve represent non-monotonic, and this one is nothing but a differential non-linearity. This represented as DNL. So it is the maximum of difference in each of the conversions current code width and the ideal code width. Okay. So here you can see the DNL value is -0.25. So if there is no difference, you will get 0. So if you have like this, it will be plus 0.25, and it is not more than plus or minus 0.5 LSP. Okay. So next, let me go for the stability. So the performance of the converter changes with the temperature, age, and power supply variation. So all the relevant parameters such as offset, gain, linearity, error, and the modicity must be specified over the full temperature and power supply ranges. So next one is accuracy. So absolute accuracy is the maximum deviation between the actual converted output and the ideal converted output, whereas the relative accuracy is the maximum deviation after the gain and offset error has been removed. So usually the data sheets will specify your relevant relative accuracy by removing the gain and offset error. Okay, so the accuracy of the converter is also specified in terms of LSP increment or percentage of full scale voltage.